In this video, we're going to bring together the two topics we've been studying, polynomial division and graphing polynomial functions. As we've discussed, a polynomial graph is formed by reconciling two major elements, end behavior and x-intercepts. X-intercepts, that is, the zeros of the polynomial function, are found by setting our polynomial function equal to 0 and solving for x. Anytime there is an exponent of 2 or above in a polynomial, we have to factor the polynomial in order to solve this equation. However, the more complicated the polynomial becomes, the more difficult it is to factor, and realistically speaking, once the degree of the polynomial is more than 3, we don't really have a consistent factoring technique at all. This is why we introduced polynomial division. Factoring is really the same thing as division, but instead of just throwing away everything and keeping the answer, we keep both the expression we divided in as well as the quotient, which again we think of as the answer for the division. These two components become factors for the polynomial that we divided into. The polynomial we're dividing into is typically the polynomial we're thinking about trying to graph. So to find our zeros when we can't factor, one of the easiest and fastest techniques to use is synthetic division. We can check whether or not a number is a zero of a polynomial using synthetic division. However, we don't yet know which values to check if we aren't given any to start with. Without any additional prior information, we theoretically would have to check all numbers, literally every real number. And statistically speaking, if we just have a random polynomial, the likelihood of ever finding an x-intercept when we're blindly picking and checking numbers is next to 0. So synthetic division will really only work if we have some way to narrow our pool of candidates. This is where the rational zeros theorem comes in. The rational zeros theorem tells us how to generate possible rational zeros to check. Essentially, this theorem will give us a good starting point for synthetic division that we can find just by comparing some numbers in our polynomial. So here's the rational zeros theorem. The theorem says, given a polynomial f of x, each possible rational zero, keyword is possible, each possible rational zero is of the form p divided by q, where p is going to be a positive or negative factor of the constant term of f of x. In other words, when we write the terms in order, this is going to be the number, the individual number that's added or subtracted at the end of the polynomial. So that's going to generate the numerator for our possible rational zeros. Q, the denominator, is a positive or negative factor of the leading coefficient of f of x. So again, if we write f of x from highest to lowest exponent, this is going to be the coefficient for the first term in our polynomial. Now, what does rational mean? Rational means able to be written as a finite or repeating decimal. So essentially anything you could write as a fraction is a rational number, but if we have it as a decimal, it's going to be a decimal that repeats in the same way forever or terminates at some point. So the rational zeros theorem gives us a way to generate the possible rational zeros that we can then check using synthetic division. So let's look at an example. So we just want to list the possible rational zeros of this function. We're not asked to actually find the real zeros. We're just asked to determine what are the possibilities based on what we now know about the rational zeros theorem. So the rational zeros theorem tells us that our possible rational zeros are going to be of the form p divided by q, where p is going to be a factor of the constant term, in this case 10, and q is going to be a factor of the leading coefficient, which in this case is -2. So the next step is to determine what are the factors of 10 and what are the factors of -2. In other words, what integer numbers divide into 10 and into -2. Now, one thing we need to keep in mind is that both positive and negative versions of each integer divide into each of these numbers. So when we list out the factors, we're going to put a plus or minus in front of them to indicate that both the positive and the negative version are possibilities. So the things that divide into 10 are going to be 1, 2, 5, and 10. And then we need to have the positive or the negative version of each of those. And then the things that divide into -2 are going to be 1 and 2, both positive and negative. So essentially what we've now generated is we've generated a list of all the possible numerators and all the possible denominators. So this is not a single number. This is a way of listing out all the different numbers that we could combine. So the next step, once we have this list of all of our separate factors, is to come up with all the different combinations where we could combine one of the numerators with one of the denominators. So the way I like to go about doing this so I don't miss anything is I like to start with the first denominator. So the first denominator is going to be positive or negative 1. And then I'm going to take every possible numerator combined with that first denominator. So I like to start this way because, as you'll see as we continue to do some more examples, when we're listing out numerators and listing out denominators, the first number we always list in the list is going to be positive or negative 1. So if we take all our numerators divided by that first denominator, which is positive or negative 1, then the first things we put in our list are going to be integer numbers. They're not actually going to be fractions. So if we're making a list of things we want to check, ideally the easiest numbers to check with synthetic division are going to be numbers that aren't fractions. So if we start our list by taking 1 as our first denominator, the first things in our list are going to be whole numbers or integer numbers. So we take 1 divided by 1, 2 divided by 1, 5 divided by 1, and 10 divided by 1. So that gives us positive or negative 1, positive or negative 2, positive or negative 5, and positive or negative 10. So we'll make the list in just a second. So that's all of our numerators combined with our first denominator. Now we go to our second denominator, which is 2, and then we want to take each numerator combined with that denominator. So 1 over 2, okay, so 1/2 is a possibility. Then we go to 2 over 2. But we don't actually have to list 2 over 2. If we were to reduce 2 over 2, it reduces to 1. And 1 is a number that's already in our list. 5 over 2 is a new one, so we'll add that to the list. And then 10 over 2 again reduces to 5, which is something we already have in the list, so we don't write it again. So our list of possible rational zeros is 1, 2, 5, 10, 1/2, and 5/2, both the positive and the negative version of each of these numbers. So what this means worst case in terms of checking numbers with synthetic division, we have to check, let's see, 2, 4, 6, 8, 10, 12 different numbers. Any other rational number that's not in this list cannot be a rational zero of our function. So essentially, worst case, we check 12 of these, and this is a completely exhaustive list. So if none of these work, we know we don't have to check any other numbers that are rational in form. Now we need to keep in mind some limitations of this theorem. One thing we need to keep in mind is that the theorem does not tell us that the polynomial must have a rational zero. Instead, it just tells us that if it does have a rational zero, then it's of the given form. In other words, when we generate our list, these are all the possibilities. Realistically speaking, it's possible that we could check all of those numbers using synthetic division and none of them will work. However, if that happens, we know that we don't have to keep checking other rational numbers. So it gives us a finite list to check, but unfortunately, it's not a guarantee that anything in the list will actually work. It just says that nothing outside of the list will work. Also, the theorem does not give us any information about irrational or complex zeros. Remember, we checked some of those kinds of numbers using synthetic division, so we know we can use synthetic division to check them. However, the rational zeros theorem doesn't give us any information about what kinds of irrational or complex numbers might work. Now, the good news is typically, if we're going to have zeros that are irrational or complex, we're going to get those near the end of the problem. So we generate our rational zeros, we check them using synthetic division. Once we can simplify our problem a little bit, we can eventually typically use the quadratic formula, and the quadratic formula is going to give us any irrational or complex zeros that our function has. So in general, procedurally speaking, we check each of our possible rational zeros using synthetic division, and then if we find one, we can start with the quotient. In other words, we canceled out one zero, we start with what's left over to continue searching for more. Now, one thing we need to keep in mind is that it's possible that a polynomial will have a 0 with a multiplicity greater than 1. We looked at this situation before when we were talking about graphing polynomial functions. Multiplicity tells us what's going to happen on the graph at that x-intercept, and depending on how our polynomial is factored, if a factor is repeated, then that particular 0 has a higher multiplicity than 1. So from our standpoint, if we're not factoring, but we're checking numbers with synthetic division, what this essentially means is that a number can divide into our polynomial more than once. So if we find a 0 that works, it's possible that it could actually work more than once. So if we run into one that works, we may want to check that 0 again, just dividing it into the quotient to see if it divides in more than once. In addition to the rational zeros theorem, there's also a couple of other theorems that are typically helpful when we're trying to find zeros. So the first one is called the fundamental theorem of algebra, and it gives us information about how many zeros we should find. So if our polynomial f of x has degree n, then we will have exactly n zeros, provided that we include all rational, irrational, and complex zeros, and that we count each zero according to its multiplicity. So we include all our different zeros that we find, and if we find one that's repeated, say we find one that occurs twice, we have to count it twice. But if we add up all the ones we find, then we expect to find exactly n of them. So for quadratics, there are always going to be 2 zeros. For cubics, there are always going to be 3. If our degree is 4, we're always going to find 4 zeros, so on and so forth. Another helpful theorem is called the conjugate zeros theorem, and this relates to complex zeros if we find any complex zeros. So if a plus bi, that's just the generic form for some complex number, if this is a 0 of our function, then its conjugate, its complex conjugate, which is a minus bi, in other words, if we flip the sign for the second term, this is also going to be a 0. So another way of stating this theorem is that complex zeros always come in pairs. You'll never find a single complex zero. You'll always find at least 2. So you could have 2 complex zeros, you could have 4, you could have 6, but you could never have just 1 or 3 or 5. They always come in even groups, even clusters. So if you find one complex zero, you know you're automatically going to have another one for your problem. So we're going to try a few of these using our synthetic division, using this idea of multiplicity, and then also using other factoring techniques. Once we get down to something that's quadratic, then we can factor, we can use the quadratic formula to find any remaining zeros so that we find all n zeros of our polynomial function. Okay, here's our first example. So we want to find all zeros of f of x is equal to x cubed minus 4x squared plus 3x plus 2. So we know based on that number of zeros theorem that because our highest exponent is 3, once we find all zeros and count them according to their multiplicity, we should have exactly 3 zeros for this problem. So let's start by using the rational zeros theorem to find our list of possible rational zeros. So possible rational zeros are determined by taking all the factors of the constant term, in this case 2, and dividing by all factors of the leading coefficient. Now notice we don't actually have a coefficient written in front of the highest exponent term, so it's an understood 1. So it's going to be the ratio of factors of 2 divided by factors of 1. Well, the only things that divide into 2 are 1 and 2, and then the only thing that divides evenly into 1 is itself. So plus or minus 1, plus or minus 2, each of those divided by 1. Well, since our only denominator is going to be positive or negative 1, the only rational zeros we could possibly have are going to be integer numbers, positive 1, negative 1, positive 2, and negative 2. So worst case, in this problem, we do 4 synthetic divisions, and after that, we don't actually have to check any more rational zeros. Based on the rational zeros theorem, these are the only ones that could possibly work. So now we just start checking using synthetic division. Now remember, with synthetic division, you have to make sure your terms are in order, and you have to make sure there are placeholders for any terms that are missing. So that still applies. Make sure you take care of that before you just list out your coefficients for synthetic division. So I like to start with just your smallest, easiest numbers to check. So let's start with positive 1. So positive 1, and then we list out our coefficients for our polynomial. So bring down the 1. 1 times 1 is 1. Negative 4 plus 1 is negative 3. 1 times negative 3 is negative 3. Combine and we get a 0. 1 times 0 is 0. Then combine, we get a remainder of 2. So 1, the number 1, is not a 0 of this polynomial because our remainder from synthetic division is not 0. 1 does not divide in evenly. So now let's check negative 1, dividing negative 1 into the same polynomial. So bring down our 1, we get a negative 1, negative 5, positive 5, 8, negative 8, and we get a remainder of negative 6. So again, non-zero remainder, negative 1 doesn't work. Now let's check positive 2. Bring down the 1, 2 times 1 is 2, we get a negative 2, negative 4, negative 1, negative 2, and we get a remainder of 0. So that means x equals 2 is one of the zeros of our polynomial. And what we also know, we know this divides in evenly, and we know that when we divide this in, what we're left with is now x squared minus 2x minus 1. Once the quotient from synthetic division is quadratic, which it is in this case, we don't have to use synthetic division anymore. Then we have other techniques we can use. So the nice thing about quadratics is potentially we could factor them, but even if we can't, we can always use the quadratic theorem. You certainly could continue checking with synthetic division, but in a lot of situations you're going to do that only to find that none of the other numbers in the list work, and you're still going to have to resort to the quadratic formula, worst case. So we're continuing our problem, factoring this polynomial, but now we're starting with the quotient from that successful synthetic division, which was x squared minus 2x minus 1. Now, if we wanted to factor this, we're looking for things that multiply together to give us negative 1, but also add together to give us negative 2. There aren't any integer numbers that do this, which means that this particular polynomial, this particular quadratic, does not factor. So we have to use the quadratic formula in order to continue the rest of this problem. So make sure you write down the quadratic formula in its basic form, no numbers plugged in, first before you do anything else. Then we're plugging in what we have as a, b, and c. So a is 1, b is negative 2, c is negative 1. Plug it in, and then if you need, take a moment, pause the video, make sure you can simplify this algebraic expression so that you get 2 plus or minus the square root of 4 plus 4 over 2. Then we keep simplifying, so combine everything under the radical. We also need to simplify the radical if possible. So we're looking for perfect squares that divide into 8. In this case, 4 divides into 8, so we split 8 up into 4 times 2. Take the square root of the 4, so square root of 8 simplifies to 2 times the square root of 2. Now, notice that each of the terms in this problem has a common factor of 2. There's a 2 outside of the square root of 2, and then the first term has a 2. Our denominator is 2 as well. So we can divide out that common factor from each of the terms, and we're left with 1 plus or minus the square root of 2. So that gives us our 2 remaining zeros. These are irrational numbers. They're not complex. There's no I in the problem, but these are irrational numbers. So in total, our list of zeros is 2, that was our only rational zero, and then 1 plus the square root of 2 and 1 minus the square root of 2. So when you make an actual list of the zeros, you're going to leave these irrational zeros in this form. This is the exact form of the irrational zeros. If you're also wanting to specifically graph this polynomial function, that's when you would take those rational zeros and plug them into your calculator and get an approximation for what those exactly are. Once you have an approximation, then you can put them on your graph and you can graph using those as x-intercepts. Let's try another one. So we want to find all zeros of f of x is equal to 2x to the fourth plus 5x cubed minus 2x squared minus 11x minus 6. So again, based on that number of zeros theorem, because our highest exponent is 4, now we expect to have 4 zeros counted by their multiplicity. So start with our rational zeros theorem, list out the possibilities, all the factors of negative 6 divided by all the factors of 2. So our possibilities that divide into 6 are 1, 2, 3, and 6, and then 1 and 2 divide into 2. So we make a list of all possible numerators combined with all possible denominators. Start with the first denominator, 1. So each of the numerators over 1 is just an integer number, plus or minus 1, plus or minus 2, plus or minus 3, and then plus or minus 6. If we combine numerators with the second denominator, we have 1 over 2. 2 over 2 is 1, so we don't list that again. 3 over 2 is new, so we add that. 6 over 2 reduces to 3, which we already have, so we don't list it again. So this is our list. Worst case, we do 12 synthetic divisions, which admittedly will take a while if we have to do that, but it beats blindly picking and checking numbers, which in theory we could do forever and never find anything that works. So start with positive 1, see if positive 1 divides in. Make sure again that you have all your terms in order, all your placeholders if you need any. In this case we don't need any, so we can just start working. So bring down the 2. 1 times 2 is 2. Then we get a 7. 1 times 7 is 7. 5. 1 times 5 is 5. Negative 6. 1 times negative 6 is negative 6. Be careful, it almost looks like these cancel, but they don't. If we combine them, we get a negative 12. Because that's a non-zero remainder, positive 1 is not a zero of our polynomial. Now let's check negative 1. So bring down your 2. Negative 1 times 2 is negative 2. Then we get a 3, negative 3, negative 5, positive 5, negative 6, and positive 6 this time. So we combine on our last column, and we get a remainder of 0, which means that negative 1 is one of the zeros, one of the x-intercepts of this particular polynomial function. Now let's see what we're left with. Remember, our quotient is the bottom line. Those are the coefficients for the terms in our quotient. So we have 2x cubed plus 3x squared minus 5x minus 6. So because the quotient is not quadratic, it's not something we immediately have a technique to factor, this is when we want to continue using synthetic division. But we're going to use synthetic division now with the quotient instead of the original polynomial we started with. So we found 1, 0. Now we're looking for the rest of them. We're going to continue synthetic division because our quotient is not yet quadratic. So one thing we need to take into account is it's possible that negative 1, the 0 we just found, could have a higher multiplicity. So we want to check it again, but make sure you check it using the quotient. If we check it with the original problem, then of course it's going to work. We already determined it worked. We want to check it with what's left over to see if it divides in again. So now we're dividing negative 1 into our quotient from our first synthetic division. So bring down the 2. We get a negative 2. Combine, we get a 1, negative 1, negative 6, positive 6, and then we combine for a remainder of 0. So negative 1 actually works twice. We only have one intercept corresponding to that, but the multiplicity of that intercept is higher than 1. It's now 2 in this case. So we're left over with 2x squared plus x minus 6. Once our quotient is quadratic, we stop our synthetic division and we just continue the problem using either factoring or the quadratic formula. So it turns out this particular quadratic actually factors. You can certainly use the quadratic formula, but you don't have to here. So our factorization is 2x minus 3 times x plus 2. Now my advice is take a minute, pause the video, make sure you know how to factor this, or make sure you can complete the rest of the problem using the quadratic formula. It's up to you. But if you plan on factoring, make sure you know how to get this factorization on your own. So if we were to set each of these factors equal to 0, our remaining two zeros would be 3/2 and negative 2. So our list of zeros, according to their multiplicity, negative 1 with a multiplicity of 2, and then positive 3/2 and negative 2. So our original function had a degree of 4. We expect to get 4 zeros as long as we count according to our multiplicity. So in this case, we do have 4 zeros because a negative 1 is repeated twice. Let's try one final example. So we want to find all zeros of f of x equals x to the 4th minus 2x squared minus 3. In this example, we're essentially going to see what worst case looks like. So if you can deal with an example like this, then you can pretty much do any problem that we're going to be doing. So we'll start with our list of rational zeros. Factors of -3, our constant term, divided by factors of 1, our leading coefficient. So for -3, 1 and 3 divide in, and then for 1, 1 divides in. So our list is fairly short. We could check +1, -1, +3, and -3, but anything outside of that list we don't have to check. So notice with this particular polynomial, everything's in order, but we need some placeholders. So make sure you put a placeholder in for the cube term and for the x term. So let's check +1 first, and again, make sure you put your 0 placeholders in. Bring down the 1, 1 times 1 is 1. Bring down the 1, we get another 1, -1, -1, -1, -1, and we get a remainder of -4. So because we have a non-zero remainder, 1 doesn't work, we can cross it off the list. Now let's check -1. Bring down the 1, we get a -1, -1. Now we get a +1, the signs flip, -1, +1 again, +1, -1, and again a remainder of -4. So -1 is not a 0. Now let's try 3. Bring down the 1, we get a 3, we have a 3 again, now we have a 9, 7, 21, 21, and then 3 times 21 is 63. Combined, we get a remainder of 60. So again, +3 doesn't work. So let's see if our last one, -3, works. Bring down the 1, we get a -3, -3, +9, 7, -21, and then -3 times -21 is +63. Again, combine, and we also get a remainder of 60. So we made a list of rational zeros. We only had 4. We checked all 4 with synthetic division, and none of them work. Well, does that mean there's a problem with the problem? Not necessarily. But looking at the degree of our polynomial, it's a degree 4, we know we should have 4 zeros. So where are they? Where do they come from? Well, if they're not rational zeros, then we know that all zeros must be irrational or complex numbers. So even though we checked all our rational zeros using synthetic division, none of them worked. That means we're going to have to use some other type of technique to figure out what our zeros are. They're there, they just aren't determined as part of the list of rational zeros. So believe it or not, we can actually factor this particular polynomial even though it's not quadratic. It just so happens that this polynomial is what we call a quadratic in form polynomial. So it's something of the form where there's something squared, and then the middle term is whatever that something is, and then we have a constant tacked on to the end. So it's not quadratic, but it's quadratic in the sense that whatever is in the middle, well, that exact thing is squared at the front, and then like in all quadratics, we have a constant term at the end. So the question mark here is representative of x squared. Notice that we have an x squared in the middle, and then x to the 4th could be rewritten as x squared squared, and then we have our -3 constant tacked on to the end. So this again is what we call quadratic in form. It's not strictly quadratic, but we can rewrite it as a quadratic essentially if we take into account what's taking the place of just the standard x in a quadratic. So what we're going to do is we're going to make a temporary substitution in place of whatever is taking the place of what we would normally have as an x in a quadratic. In this case, what's in the way is the x squared. So everywhere we have an x squared, we're going to make a temporary substitution and put the variable a in place of that. You can pick any variable you want, just don't pick x. It's got to be something other than x. So now this becomes a squared minus 2a minus 3. Keep in mind this is completely legal as long as we remember at the end of the problem that we're not talking about a's, we're talking about x's, so we'll have to resubstitute everything in place of a. Now that this is quadratic, we can actually factor it using our factoring techniques for quadratics. So we want two numbers that multiply to give -3 and add to give -2. So that would be -3 and +1, so we have this particular factorization. So split it up, we get a equals 3, we get a equals -1. Now 3 and -1 are not our answers to our problem. A is equal to each of these, but what we want is x. We want to know what x is equal to. So we need to resubstitute that x squared in place of the a. So x squared is equal to 3 for our first solution. We take the square root of both sides, and we get x is equal to positive or negative square root of 3. So this gives us 2 irrational zeros. Now go to the a equals negative 1. So put the x squared in place of the a. X squared is equal to negative 1. Take the square root of both sides. So we get x is equal to plus or minus square root of negative 1. Well, if you remember, we defined the square root of negative 1 as I, specifically to deal with that whole issue of taking a negative of square root. We specifically assigned this value the letter I, the imaginary unit. So our other two zeros are positive or negative I. And if you remember, we had that conjugate zeros theorem, which said if we have an imaginary or a complex zero, we have to at least have two. They always have to come in pairs. So this is our paired complex zero. Because there's an I, it's complex, we have both a positive and a negative version. So the plus version and the minus version are considered to be complex conjugates of one another. So if you put all this together, we actually have 4 zeros. We have the positive square root of 3, the negative square root of 3, positive I, and negative I. So one thing you need to take into account with an example like this is the irrational zeros do represent x-intercepts. We can graph we can graph the square root of 3. We can graph the negative square root of 3. We'll approximate them to get a sense of where they lie on the graph, but they represent x-intercepts somewhere on the coordinate plane. However, I and negative I, our complex zeros, do not give us x-intercepts. They are zeros. They are numbers that if we were to plug into our function, they would give us a 0 at the end, but they don't represent x-intercepts. They just represent zeros in the sense that they algebraically solve the equation f of x is equal to 0. So this really is worst case. We generate our list of rational zeros and none of them work. Keep in mind, it is possible that can happen. The rational zeros theorem, again, does not tell us that we have to have rational zeros. It just says that if we have any, they're going to be something in this list. So worst case, we check everything using synthetic division and none of them work. Well, if we run into a situation like that, it could be any number of different possibilities, but for our purposes, because we're going to keep things fairly simple, if you run into a situation like that, look for something that may be able to be factored using some type of substitutionary technique, just like the one we used here. So let's summarize everything we learned in this video. We learned that for any polynomial function f of x, the number of zeros is going to be equal to the degree of f of x. So whatever our highest exponent is in the problem, if we're looking for zeros for that particular polynomial in order to graph, we're going to have the same number as the highest exponent in the polynomial. In order to find all our zeros, first thing we do is generate the list of possible rational zeros. That's going to be factors of the constant term, the number added or subtracted at the end, divided by factors of the leading coefficient, which is the number in front of the term with the highest exponent. So we generate all the different combinations of possible numerators, possible denominators, and this gives us our list of numbers to check. So we check using synthetic division. Specifically, we're looking for a remainder of 0. So we're doing synthetic division with our rational zeros from our list, and we want to see if the number at the end of our synthetic division is 0. After a 0 is found, we continue checking now using the quotient from that successful division. So we may need to check the same number again. It's possible it could divide in more than once, but regardless, we keep using synthetic division until the quotient is quadratic. Once the quotient is quadratic, then we want to find any remaining zeros by factoring, if factoring is a possibility, or if it's not, we're going to use the quadratic formula. Worst case, there may be no rational zeros. In other words, we check everything in our possible rational zeros list and none of them work. This means that all our zeros are going to be either irrational or maybe complex or some combination of the two. In this case, check for something like a polynomial that might be able to be factored as a quadratic in form, like the last example we did where we had to make a substitution.